Welcome back to another physics class. In today's lesson, we're going to discuss work and power. Here are some of the definitions. Work is a parallel force that is applied over a given distance, causing displacement. So the force that is applied has to be in the same direction, and that must cause a movement and essentially a displacement of the object. Power is the rate at which work is done. Essentially, how quickly is your work done? And we've talked about energy before. Energy is the ability to do work. It's a measure of the system's capacity to do work. Here are some of the variables and the units which we'll be working with. W in an equation is going to stand for work. However, a W after a number will be the units for power, which stands for watts. So when we're talking about work, the variable which you see in the equation is W. That stands for work. The unit for work is J, or joules. The variable P stands for power, and the unit for power is W for watt. Again, if you think about electricity, we talk about kilowatts per hour, so it's watts. Now again, that W is the one that you would see after coming numbers. So a W after numerical values means that it's watts, and it actually stands for power. And we're going to talk about energy. Most energy will be defined into two categories as kinetic or potential energy. The variable for energy is E, and the units for energy is also J, or joule. And we'll get into that later. All right, so the two equations that we'll be working for is work is equal to FD, the force, times the distance. And we've got power is equal to work divided by time. Remember that the work is a force applied over a certain distance causing displacement, and power is the rate at which work is done. So the work divided by the amount of time taken to do it. So over here, we still see some of the same variables. Force, again, this is going to be your newtons. Now, D is really for displacement. Sometimes it gets referred to as distance. And sometimes, depending on the equation that you may see it, it might be used as S. In our district, we just use W equals FD, but if you ever come across W equals FS, it's the same thing. And the unit for any kind of distance or displacement is always going to be in meters. And finally, we have time. In time, you got to make sure that you're in seconds. Moving on to energy. Now, energy, again, the unit for that is joules, which is the same as the unit for work. And it's the capacity or the ability to do work. Like I said earlier, they get broken down into two major categories, and it's either kinetic energy or potential energy. We'll discuss all of these in a later time and in depth, but the basic overview for this is kinetic energy is the energy of motion, and you must be moving. And moving objects can do work. Now you see a little asterisk for both of those in the middle. And the reason for this is it can transition. But again, this is the most basic review. So as of right now, we're just going to consider kinetic energy as any energy that is moving, and potential energy is anything that is not moving. So what is potential energy? Potential energy is stored energy based on position or height. Again, this is regarding an energy or an object that is not in motion, whereas kinetic energy is purely for an object that is in motion. When we discuss potential energy, there's a potential there, but it hasn't done any work yet. It's kinetic energy that does work. In our equations, later on, you'll see as KE or PE. Those will stand for kinetic energy and potential energy, respectively. And the units for both of those energies, or all energy for that matter, is always going to be J, or joules. All right, so work. Work is equation 20 in our formula sheet, and the equation is W is equal to F times D. Now remember that F can be replaced by MA, so W is also equal to M times A times D. And as I said earlier, sometimes depending on your source, depending on the equation that you may see, W is equal to Fs. That S stands for displacement. So it's the same thing as the D. When is work done? Work is done when you have applied a parallel force, meaning the force is applied in the same direction as the movement. Of course, you got to have movement, which means you got to have displacement. Without any movement and displacement, there is no work done. Looking back at the equation again, W equals F times D. Here's my cheesy way of helping you guys out. And it's essentially when you have to do work, you get mad. So imagine if your teacher assigns you a lot of work. Well, you get mad. But the reason for that is because, F is equal to MA. So it's easy to remember it that way. But when you come across problems and there's no force listed, remember that you get mad because you got to do an additional step. So work is equal to FD, or you could think about it as when you do work, you get mad. So W is equal to mad. The units for work, again, it can be joules or newtons times meters, because if you think about it, force is Newton, distance and displacement is in meters. So that's where you see the newtons times meters. And 1 joule is also equivalent to 1 newtons times meters. All right, let's go ahead and look at some of these scenarios. Scenario 1, I pick up the ball. Scenario 2, I drop down the ball. Scenario 3, I push down on the ball while it's on the ground. Was there any work done? And if so, which scenario? If I pick up the ball twice as fast, am I doing twice the work? And why do I get tired if I've not done any work? So let's take a look at these scenarios. Was there any work done by me? The answer to that is, well, for scenario 1, yes, that was work done by me. I picked up the ball. It was a vertical force. It was in the same direction as the direction of the ball that moved and was displaced vertically. So that's work done by me. In scenario 2, I didn't personally do any work. Instead, I just dropped it. So the work was actually done by force of gravity, not by me. And in scenario 3, even though I pushed down on the ball didn't move. There was no displacement on it. So no distance, no displacement, no movement means no work was done. If I pick up the ball twice as fast, am I doing twice the work? No, I'm doing the same exact amount of work. What changes, though, is my power, because power depends on time, as power is the rate at which work is done. And finally, why do I get tired if I've not done any work? Well, you can exert force, but it doesn't mean that you actually did anything productive. So if you never moved anything, you could expend all the energy you want, but you didn't do any and cause no displacement, then there was no work. Moving on to power. So now I've highlighted a couple of different W's. Power is equation number 22 in our equation sheet. Remember that the units for power is watts, or a capital W. It could also be joules per second because it's work divided by time. So the units for work was J. That's where you see the joules per second because it's work divided by time. Now, in the green one, in the equation, that W is the variable representing work. What's highlighted in yellow would be what would come after numerical values, and that represents the units of power. So make sure you don't get this confused. Equation number 2, power is equal to work divided by time. Of course, we said work is essentially a force times a distance. So when you get power, it's FD is equal divided by time. And when you don't have force, then you got to go a little step further. So its power is equal to mass times acceleration times the distance or displacement divided by time. Make sure that you just multiply the MAD portion at the very top first before dividing by any time value. All right, so power is measured in watts. It could also be measured in joules per second because of work. And sometimes we also refer to it as horsepower. So 1 watt is equal to 1 joule divided by per second, and 746 watts is equal to 1 horsepower, and 1,000 watts is equal to 1 kilowatts. Now, you don't have to memorize these. If they come up in a problem, we'll provide it to you, but it's good to know about the ratio. All right, so time to go ahead and do some problems. You carry a 3 kg pack of bottled water across the store for 2.5 minutes, and you wait in line holding it for 30 seconds before you get tired and drop it. You then lift the pack upwards for 157 centimeters, place it on the counter. How much work did you do at the store? If you're planning on skipping through, I highly suggest that you pause, go back, and answer these problems on your own before going forward. All right, let's look at this problem. What are we solving for? We're solving for work. The variable is W. The units, of course, joules. Is time needed for work? No. Time is only needed for power. Now, if you drop something, did you actually do any work? No. Again, that's the gravity doing that work for you. So you personally didn't do any work by the object falling down. Speaking of work, it's also an applied force in the same direction of displacement of the object. So when you're holding it and moving it across the store for 2.5 minutes, and you wait in line and holding it for 30 seconds, none of that is actually considered work, because the force to move something across the store, again, you're holding that object upwards. So it's a vertical force, but you're moving horizontally. So that's not parallel. Likewise, when you're holding it and you're standing in line, you're applying force to hold it up. However, that's not causing any kind of displacement on the object. So no displacement means no work done there. The only work that we've done is from the displacement that we have from ground up to when you put it up to the counter. So we have that displacement there. It's in centimeters, and you have to convert it into meters. So hopefully you caught on to that. And do we have any force listed? There's no force listed in this problem. And where there's no force listed, you got to do an additional step, which means you get mad. So W's are unknown. See, with the unit of joules, force is not mentioned. So again, you get mad. Mass is 3 kilograms. Acceleration is 9.8 meters per second squared. Remember that gravity, acceleration due to gravity, is negative 9.8 meters per second squared. But this is an upwards going for Fn. So it's positive here. And our displacement was, when we converted, 1.57 meters. So we plug it into our equation of W equals Fd, and we swap the values. So 3 for our mass, 9.8 for acceleration, 1.57 for our displacement, and we get the work as 46.16 joules. Number 2, if a man with a mass of 90 kg puts on a 15 kilogram backpack and climbs a ladder for a displacement of 20 meters in 40 seconds, how much power did he use? So just like the previous one, go ahead and pause this, write it all out, solve it first, and then check to see where you stand. Again, if you're skipping through, this is one of those trickier ones, so please pause it and then go forward. All right, so what are we solving for here? We're solving for power. The variable is P, the unit for power is W. Do we need time for power? Yes. Is there any mention of joules or work being done? No. They didn't mention any work. They didn't mention any joule. So we don't have that yet. Do we have a displacement? Yes. We had a vertical displacement of 20 meters. Do we have a mass? Yes. We actually had 2 of them. The man has a mass of 90 kilograms, and he puts on a backpack of 15 kilograms. So there's 2 masses, and when they're added together, you got to combine them, because now the man with the backpack has a total mass of 105 kilograms. And do we have a force listed? There's no force listed. So if there's no force listed, which means you got to do additional step, so you get mad. All right, so we're solving for power with the units of watts, or W. The force is not mentioned, so we're going to go ahead and get mad. The mass, of course, the man had a mass of 90 kilograms, and he put on a backpack of 15 kilograms. So you combine the two because his current mass is 105 kilograms, and that's what he's climbing up the ladder with. The acceleration, against a vertical movement. So acceleration of gravity is negative 9.8, but we're offsetting that and going upwards. It's 9.8 meters per second squared. The distance, or the displacement, was 20 meters vertically, and the time that we did it in was 40 seconds. So our equation is P is equal to work divided by time. Work, of course, gets replaced by FD, which we don't have. So it gets replaced by mass times acceleration times displacement divided by time. It's a good habit to always make sure that you multiply the top portion before just dividing. So It's 105 for our combined mass times 9.8 times 20 meters for our displacement. All of that multiplied together and then finally divided by the 40 seconds gives us a power of 514.5 watts. And finally, number 3, if 720 joules are needed to move a crate vertically for 6 meters, what is the weight of the crate? Now, this question didn't mention work or didn't mention power for that matter. However, you got to take your numerical values and you got to understand what they represent from simply the units. So we have 720 joules, and that is our work. We have 6 meters, that's our displacement. And they're asking for weight. Remember that weight is a force, and essentially it's Fn, so we're really solving for force. So F, or weight, is our unknown variable with the units of newtons. Work is 720 joules. Again, they didn't specifically mention work. You just got to figure that out from the units. And the distance and displacement was 6 meters. So our equation is W equals FD. Replace your values. 720 for the W. F is still going to remain as F. And our displacement was 6. So 720 divided by 6 gives us our force. And the force was 120 newtons. Of course, that is our weight as well because it's the Fn, or the normal force, of the object. So these are the type of sample problems that you're going to see. Again, there's plenty of simpler options. However, it's good to see some of these over here, especially number 1, and understanding that not all movement or not all forces are considered as work. So go back to number 1, pay attention to what I said there. Remember that in number 1, just because you're holding an object doesn't mean that you're doing any work. In order to have work, you got to have parallel force applied into the same direction as the displacement or the movement. So if it's stationary, there's no work. Likewise, as you're moving across the store, the movement is horizontal, but the force that you apply to hold that object is vertical. So they're not parallel. So there's no work there. So these were some of the better examples, some of the what might be a little bit more trickier. So I hope this was helpful. Have a wonderful day.